video, we're going to calculate a differential. So we're given a function, f of x is the natural log function, and the first thing we're asked to do is to find the differential, dy, of f. Just getting used to that vocabulary. That's basically, since it's not asking me to evaluate it at a point, that's asking me to find a formula for calculating dy. Okay. And remember, we're thinking of dy as a variable representing the rise, or the vertical change between points on the tangent line. Dx we're thinking of as a variable representing the run, and we know the relationship between these things. I know that rise is just slope times run. So it's a familiar concept with some new vocabulary and some new notation. So the rise is dy, the slope is just f prime of x, and the run is dx. This is the generic formula for calculating a differential. All I need to do here is plug in the derivative of the specific function that I was given. Since f of x is the natural log of x, I know that its derivative is 1 over x. So there's the differential of the natural log function. Okay, now we're asked to calculate that, so we're asked to get a numeric value for it if x is 1 and dx is negative 0.02. So notice, this is one of the first times you've maybe seen this. This is essentially a function of two variables. There are two things I need to plug in to get a numeric value. I need to know the x value of the point of tangency. I need to know the slope of which line are we talking about, because there are infinitely many points on the graph of the natural log of x. Each of them has a different tangent line. So I need to know which slope of which tangent line are we talking about. And then I also need to know how much are we changing x. How far are we moving away from that point horizontally? And then I can calculate how much we would move away on that line vertically. Okay, so I'm still calling it dy. This is the generic formula for the differential. This is going to be the differential evaluated at this for these particular values. So I'm just plugging in 1 for x and negative 0.02 for dx, and so we'll get negative 0.02 is our answer to the second question. Turns out it's actually the same as dx was, which kind of makes sense because the slope in this case was 1. Now let's just draw a picture of what just happened. So we were working with the natural log function. Oops. And I know that at 1, that's actually the location of the x-intercept for that function. And the tangent line we just calculated has a slope of 1. Okay. Now, negative 0.02 is a fairly small distance. So what I'm going to do is over here, I'm just going to redraw a part of that picture, but sort of zoomed in. Okay, so if here's 1, negative 0.02 is telling me I'm going to go a distance of 0.02 to the left because that was negative. That would actually take me to an x value of 0.98. Making that signed distance there, negative 0.02. And what we're trying to calculate then is if we went that far to the left, what's the vertical change on the graph of the tangent line? This is what we just calculated. That dy is also a negative 0.02. We went down 0.02. Okay. Now that's all we were asked to do. Where that might be useful is if I wanted to estimate this vertical distance. This would be delta y. That's the vertical change on the function. So I know what the value of the natural log is at 1. Kind of difficult to calculate without the aid of technology what the value is at at 0.98. However, I can say, oh, if I just go 0.02 to the left, I'm going to go approximately 0.02 down. So changing x by a little bit induces a change in y, and I could estimate that using this differential.